In section 8-2, we're going to be computing confidence intervals for a population mean, but here the sigma is unknown. So our objectives are describe the properties of a student t-distribution, construct the confidence interval for a population mean when the population standard deviation is unknown, and then use the TI-84 to calculate confidence intervals. Objective 1. Describe the properties of a student t-distribution. When constructing a confidence interval, where we know the population standard deviation sigma, the confidence interval is just the point estimate x bar plus or minus the margin of error, which is z times the standard error. The critical value z, because the quantity z equals x bar minus mu divided by sigma divided by the square root of n, has a normal distribution. However, it is rare that we would know the value of sigma while needing to estimate the value of mu. In practice, it's more common that sigma is unknown. When we don't know the value of sigma, we may replace it with the sample standard deviation. However, we can't use z as the critical value because the quantity x bar minus mu divided by s divided by the square root of n does not have a normal distribution. The distribution of this quantity is called the student t-distribution. There are actually many different student t-distributions. They are all distinguished by a quantity called degrees of freedom. When using a student t-distribution to construct a confidence interval for a population mean, the number of degrees of freedom is one less than the sample size. A student t-distributions are symmetric and unimodal, just like the normal. However, they are more spread out. The reason is that S is on average a bit smaller than sigma. So, since sigma is random, whereas since S is random, where sigma is constant, replacing sigma with S increases the spread. When the number of degrees of freedom is small, the tendency to be more spread out is more pronounced. When the number of degrees of freedom is large, S tends to be close to N. So the t-distribution is very close to normal. So as N increases, then the t-distribution becomes more and more normal. And technically, when N gets greater than 300, typically, our distribution gets very close to being standard normal. So there's a new table in town called the t-distribution table, the t-table, student t-distribution. To find the critical value for a confidence interval, we let 1 minus alpha to be the confidence level. The critical value then is t alpha over 2, because the area under the student t-distribution is between a negative t alpha over 2 and t alpha over 2. And they all equal 1 minus alpha. The critical value t divided by alpha over 2 can be found in A3, in the row corresponding to the number of degrees of freedom, and the column corresponding to the desired confidence level by technology. So in this particular table, for example, if we were looking for, suppose our sample size was 5, our degrees of freedom would be 1 minus, or 5 minus 1, which would be 4. And if we were looking at a 95% confidence interval, we would actually be looking for this number. The reason why is because 0.025 is in the right tail, and in the left tail it's also 0.025. You add them up and it's 5%. So a simple random sample of size 10 is drawn from a normal population. We want to find the critical value t alpha over 2 for a 95% confidence interval. So the solution is the sample size is 10, so the number of degrees of freedom is 9. We consult the table A3 and look for the row where the degrees of freedom is 9, and in the column with the confidence level of 95%. It turns out, in this particular case, well, when we match those up, we get a value for t to be 2.262. Well, the table is not always the best to use in many cases, so we have to make the best of it. Well, sometimes we have to round up. So, if the desired number of degrees of freedom isn't listed in table A3, then if the desired number is less than 200, we use the next smaller number in that table. If the desired number is greater than 200, we use the z-value found in the last row of A3, or use just table A2. So as you can see here, the last row of the table actually shows the confidence level for those that would be found under the standard normal curve. So here are our assumptions. The assumptions for constructing a confidence interval for mu when sigma is unknown are the following. We have this simple random sample. The sample size is larger than 30, or the population is approximately normal. When the sample size is small, less than 30, we must check to determine whether the sample comes from a population that is approximately normal. A simple random method is to draw a dot plot or a box plot of the sample. Also find the skewness measure. If there are no outliers, and if the sample is not strongly skewed, then it is reasonable to assume the population is approximately normal. And it is appropriate to construct a confidence interval using the student t distribution. This is also true when we do also know sigma as well. So the second objective is to construct the confidence interval for a population mean when the population standard deviation is unknown. So here are the steps. If the assumptions are satisfied, the confidence interval for mu when sigma is unknown is found by using the following. Compute the sample mean and the sample standard deviation. Right? Find the number of degrees of freedom, n minus 1, and the critical value from the table t alpha over 2. Compute the standard error. The standard error is the sample standard deviation divided by the square root of n, and multiply the critical value to obtain the margin of error. In this case, the margin of error is t times the standard error. So then we construct the confidence interval. It's the point estimate, x bar, plus or minus the margin of error. Then we interpret the results. So a food chemist analyzed the calorie content for a popular type of cookie. The following are the numbers of calories in the sample of 8 cookies. Find a 98% confidence interval for the mean number of calories in this type of cookie. Well, we have to check the assumption of normality, and we know that we have a simple random sample. Because the sample size is small, the population must be approximately normal. In this case, a dot plot indicates that there's no evidence of strong skewness nor outliers. Therefore, we may proceed. We may also want to use a box plot as well. Now we find the sample mean and standard deviation. Here, from our calculations, we have x bar is equal to 115.375 and a standard deviation of 2.2853. To continue on, the number of degrees of freedom in this particular case is 8 minus 1, which is 7. And so now we use table A3, and we find that the critical value corresponding to a level of 98% is 2.998. So we now can calculate the margin of error. The margin of error is going to be the critical value 2.998 times the standard error, which is the sample standard deviation, divided by the square root of the sample size, which is 8. The number that we end up coming up with is 2.9947. To construct the confidence interval, we know it's the point estimate plus or minus the margin of error. There's the formula for that. So we plug those numbers in that we got, which is 115.375 plus or minus 2.9947, and we get a confidence interval that the low bound is 112.4 and the upper bound is 118.4. So we are 98% confident that the mean number of calories per cookie is between 112.4 and 118.4 calories. In our second problem, a sample of 123 people aged 18 to 22 reported the number of hours they spent on the internet in an average week. The sample mean was 8.2 hours with a sample standard deviation of 9.84. Assume that the simple random sample from the population of people aged 18 to 22 in the U.S. Construct a 95% confidence interval for mu, the population number of hours per week spent on the internet by people aged 18 to 22 in the U.S. Well, we have a simple random sample of size that is large. We may proceed. So we don't have to check normality because we have 123 people. So in this case, n equals 123. So because it's greater than 30, and since it is a random sample, we may assume that the central limit theorem applies. So in this case, the number of degrees of freedom is n minus 1, which is 123 minus 1, which is 122. Since this value does not appear in the table, we will use the next smaller value in the table, which is 100. The critical value corresponding to a level of 95% for 100 is 1.984 from our table. And continuing on our calculation, we compute first the margin of error. Again, the margin of error is the critical value times the standard error. When we do that calculation, we get a number 1.7603. Now, to create the 95% confidence interval, we have the point estimate plus or minus the margin of error. In this case, the point estimate, which is x bar, is 8.2, and our margin of error is 1.7603, and it's plus or minus, so we have the following bound. The lower bound is 6.44 hours, and the upper bound is 9.96 hours. So we are 95% confident that the mean number of hours per week spent on the internet by people 18 to 22 years old is between 6.44 and 9.96 hours. Our second objective is to construct for a population mean when the population standard deviation is unknown using the TI 83 or 84. So when we use our calculator, we're going to use something called the t-interval command in the stats test area. So the first thing we're going to do is we enter in the stats key. When we press that, we come over to the test menu. You will notice that when you hit the test menu and you go down to t-interval, which is option 8, if you only have the statistics from the problem, you will only choose statistics. If you do have data and you've entered it into one of the spreadsheet L1 through L6, you're going to use the data option under the t-interval. So again, we're going to go back to the food chemist that analyzes calories for a popular type of cookie. And we saw in this particular case the following data of 8 different cookies. We want to find the 98% confidence interval of the mean number of calories for this type of cookie. So typically, if we're using the calculator, we have to check the assumptions of normality. Since our calculator doesn't do a dot plot, we will probably use the box plot process on our calculator, which is the second y equal key. So we would do that and see that there are no outliers. Then we want to make sure, of course, that we've entered the data into L1 when we go use the box plot. So we enter the data by hitting stats, hitting enter, entering it into L1. Then we press the stats key and go over to test, and we select the t-interval. Well, once we select the t-interval, option 8, we get this following menu screen. We're going to select data. Why? Because we entered the data into L1. And we're going to say for the list, we're going to put in L1. We leave the frequency 1 alone, and then we go down to the C level, which is the confidence level, and we put in 0.98. Then we hit calculate. You will notice that the first entry into our screen is our confidence level, or confidence interval. And you will notice that that confidence interval has a low bound at 112.38 and the upper bound of 118.37. In our second particular problem, we weren't given the data set. So, in this case, we can go directly by pressing stats and tests and selecting the t-interval. So in this particular case, we had a sample size of 123 people. We knew that the mean value was 8.20, or X bar was, and that our sample standard deviation was 9.84. We will put that information into our calculator. We have to make sure that the stats icon is on. For X bar, we'll enter in 8.2. The standard deviation will enter in 9.84. 0.84, and for n, we'll enter in 123. In this case, we wanted a 95% confidence interval, so for the sea level, we'll enter in 0.95. Then we'll hit calculate. The next screen shows us our confidence interval, which is 6.4436 is the lower bound, and the upper bound is 9.9564 hours. So obviously, we're 95% confident that the mean number of hours per week spent on the internet by people 18 to 22 years old is between 6.44 and 9.96 hours. So in this section, the properties of the student t-distribution should be known. Why we must determine whether the sample comes from a population that is normally normal when the sample size is smaller than 30. So we must determine whether that sample is. And then there are ways in which we check for normality. And then how to construct or interpret a confidence interval for a population mean when the population standard deviation is unknown. Well, that concludes chapter section 8-2, and then our next section that we're going to be talking about is estimating population proportions.